The universe is constantly expanding every day. But what is it expanding into? When astronomers using the Hubble Space Telescope looked at distant supernovae in the late 1990s, they discovered something that would fundamentally change our understanding of the cosmos and earn a Nobel Prize. They found that the universe is not just expanding, it is accelerating. This acceleration means that with each passing moment, distant galaxies are moving away from us, faster and faster, driven by a mysterious force we now call dark energy. This discovery was so unexpected that the teams involved spent months checking and rechecking their calculations, certain they had made an error. They had not. The universe is pulling itself apart at an ever-increasing rate. The Supernova Cosmology Project and the High Z Supernova Search Team worked independently and arrived at the same shocking conclusion. Type Ia supernovae, which serve as cosmic distance markers because they explode with consistent brightness, showed that galaxies billions of light years away were dimmer than expected. This dimness meant they were farther away than they should be if the universe were expanding at a constant rate or slowing down. Something was pushing the universe apart faster and faster. This something, dark energy, now accounts for about 68% of all the energy and matter in the entire universe. It is the dominant force shaping the cosmos on the larger scales. To understand what this means, we need to grasp a crucial detail about cosmic expansion that is often misunderstood. Space itself is expanding. This is not like objects flying apart through space after an explosion. The fabric of space, the very stage on which cosmic events play out, is stretching. Imagine a rubber sheet with dots drawn on it. As you stretch the sheet, the dots move apart, but the dots themselves are not moving through the rubber. The rubber between them is expanding, carrying them along. This is what happens in our universe. Galaxies are like those dots, and space is like the rubber sheet. The current rate of this expansion is measured by something called the Hubble constant, named after Edwin Hubble, who first measured cosmic expansion in 1929. The Hubble constant tells us how fast space is expanding. Current measurements put it at about 70 kilometers per second per megaparsec. A megaparsec is 3.26 million light years. This means that for every 3.26 million light years of distance between us and a galaxy, that galaxy is receding an additional 70 kilometers per second faster. A galaxy 10 megaparsecs away is receding at 700 kilometers per second. A galaxy 100 megaparsecs away is receding at 7,000 kilometers per second. You can see how quickly this adds up. At a certain distance, galaxies are receding faster than the speed of light. This does not violate Einstein's theory of relativity, because nothing is moving through space faster than light. Rather, space itself is expanding faster than light can traverse it. The cosmic event horizon, currently about 16 billion light-years away, marks the boundary beyond which galaxies are receding so fast that light from them can never reach us, no matter how long we wait. Anything beyond this horizon is fundamentally and permanently inaccessible to us. Every moment, more galaxies cross this boundary and disappear from our cosmic reach. The Dark Energy Survey, using the Blanco telescope in Chile, has mapped millions of galaxies to trace this acceleration in exquisite detail. They measure how galaxy clustering has evolved over billions of years, comparing the distribution of galaxies at different cosmic distances and therefore different times in the past. Every measurement confirms the same pattern. About 5 billion years ago, the expansion of the universe began to accelerate. Before that, gravity had been slowing the expansion down, as you would expect after the initial impetus of the Big Bang. But 5 billion years ago, dark energy became the dominant force. It has been winning the cosmic tug-of-war against gravity ever since, The Atacama Cosmology Telescope and the South Pole Telescope have measured tiny variations in the cosmic microwave background radiation, the afterglow of the Big Bang. These measurements reveal the universe's expansion history, written in the structure of these ancient temperature fluctuations. Combined with supernova observations and galaxy surveys, all the evidence points to the same conclusion. Dark energy is real, acceleration is happening, and our cosmic future is one of increasing isolation. What exactly is dark energy? The honest answer is we do not know. It is perhaps the deepest mystery in modern physics. The simplest explanation is that it is the energy of empty space itself, what physicists call the cosmological constant. In quantum mechanics, even empty space is not truly empty. Virtual particles constantly pop into existence and annihilate, borrowing energy from the vacuum for brief instants. This quantum foam might have a net positive energy density that pushes space apart. When Einstein first developed his equations of general relativity, he added a term called the cosmological constant to make the universe static, because at the time, everyone believed the universe was eternal and unchanging. When Hubble discovered cosmic expansion, Einstein removed this term, reportedly calling it his biggest blunder. Now, it seems the cosmological constant might be real after all. But rather than holding the universe static, it is driving its acceleration. However, there is a profound problem with this explanation. When physicists calculate what the vacuum energy should be based on quantum field theory, they get an answer that is wrong by a factor of 10 to the power of 120. This is the worst prediction in the history of science. Something is either catastrophically wrong with our theories, or there is some unknown mechanism that almost perfectly cancels this enormous vacuum energy, leaving just the tiny amount we observe as dark energy. This is called the cosmological constant problem, and despite decades of effort by the brightest minds in physics, no one has solved it. Alternative theories suggest that dark energy might not be constant, but could change over time. This is sometimes called quintessence, after the fifth element of ancient philosophy. In these models, dark energy is a dynamic field that permeates space and changes its properties as the universe evolves. Different quintessence models predict different futures for the universe. Some suggest the acceleration might slow or even reverse. Others predict it will increase, leading to a catastrophic end called the Big Rip. We will explore these scenarios later, but for now, the key point is that despite its dominance in the universe, dark energy remains one of the great unknowns of modern cosmology. The European Space Agency's Euclid mission, launched in 2023, is specifically designed to study dark energy. It will observe billions of galaxies, measuring their positions, distances, and shapes to map the universe's large-scale structure and trace its expansion history with unprecedented precision. Every new observation so far has only confirmed the basic picture. The universe is accelerating, dark energy is real, and we need new physics to explain it. The Planck satellite mapped the cosmic microwave background with extraordinary detail, revealing the universe's composition with remarkable precision. About 5% is ordinary matter, the stuff of stars and planets and us. About 27% is dark matter, mysterious particles that interact gravitationally but emit no light. And about 68% is dark energy. This last number, the dark energy fraction, is growing. As the universe expands, matter and dark matter become more dilute, their density dropping. But dark energy, if it truly is the energy of empty space, maintains constant density even as space expands. New space brings new dark energy. This means that over time, dark energy becomes increasingly dominant, and acceleration becomes increasingly pronounced. Let us consider what measurements of cosmic expansion tell us about the universe's past. By looking at distant galaxies, we are looking back in time. Light takes time to travel, so distant objects appear as they were when their light was emitted. The most distant galaxies we can see appear as they were more than 13 billion years ago, when the universe was young. These galaxies show less redshift per unit distance than nearby galaxies, confirming that in the past, the expansion was slower. By measuring redshifts and distances for thousands of galaxies at various distances, astronomers can reconstruct the entire expansion history of the universe. This history reveals a fascinating story. For the first 9 billion years or so after the Big Bang, gravity dominated. The expansion was slowing down as the mutual gravitational attraction of all the matter in the universe pulled back against the initial impetus of the Big Bang. Then, about 5 billion years ago, as the universe expanded and matter became more dilute, dark energy began to dominate. The expansion began to accelerate. This acceleration has been increasing ever since, and will continue to increase indefinitely into the future, assuming dark energy remains constant. The Baryon Oscillation Spectroscopic Survey, part of the Sloan Digital Sky Survey, has traced sound waves in the early universe that created a characteristic scale in galaxy clustering. In the first few 100,000 years after the Big Bang, sound waves rippled through the hot plasma that filled space. These waves created alternating regions of slightly higher and lower density. When the universe cooled enough for atoms to form, these density variations were frozen in place. Over billions of years, the denser regions attracted more matter and became the sites where galaxy clusters formed. By measuring the typical separation between galaxy clusters, we can trace how much the universe has expanded since those sound waves were active. This method, called the baryon acoustic oscillation technique, provides some of the most precise measurements of dark energy's effects. Every measurement confirms that dark energy is causing the universe to expand faster and faster. But what does this mean for the long-term future of the cosmos? Here is where things become both fascinating and sobering. The universe is currently filled with galaxies grouped into clusters and superclusters, connected by vast filaments of galaxies in what astronomers call the cosmic web. But this structure is temporary. Dark energy is tearing the cosmic web apart. In about 100 billion years, all galaxies outside our local gravitationally bound group will have passed beyond the cosmic event horizon. The local group consists of the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies, all bound together by their mutual gravity. This gravitational bond is strong enough to overcome the expansion of space within our local group. But beyond our local group, cosmic expansion will have stretched space so much that other galaxies will be receding faster than light. They will disappear one by one beyond the horizon, their light redshifted to longer and longer wavelengths until it becomes undetectable. Our local group itself will undergo dramatic changes. The Milky Way and Andromeda are currently approaching each other at about 120 kilometers per second. In about 4.5 billion years, they will collide. This collision will not be a violent crash of stars. Space is so vast that despite each galaxy containing hundreds of billions of stars, individual star collisions will be extremely rare. Instead, the galaxies will pass through each other, gravitationally disrupting each other's structures. They will swing around and pass through each other again. Over hundreds of millions of years, they will merge into a single, giant, elliptical galaxy. Astronomers have already given this future galaxy a name, Milkomeda, by the time the universe is 100 billion years old. all other galaxies will have disappeared beyond the cosmic horizon. An observer in Milkomeda will see a sky completely empty of galaxies. If a civilization arises at that time, they will have no way to discover that other galaxies exist. They will see a single island galaxy surrounded by infinite darkness. The cosmic microwave background will have been redshifted to such long wavelengths that it will be undetectable. Without the cosmic microwave background, without other galaxies, without any evidence of the Big Bang, future civilizations will have no way to discover the true nature of the universe. They will not be able to learn about cosmic expansion or dark energy or the origin of the universe. The evidence will have been erased by time and expansion. This leads to a sobering realization. We live at a special time in cosmic history. We exist during the brief window when the universe's past is still visible, when the cosmic microwave background can still be detected, when other galaxies still dot the sky. Earlier in cosmic history, the universe was too hot and dense for complex life. Later, it will be too empty and isolated. We happen to live during the narrow epoch when the universe can be understood by its inhabitants. This might not be a coincidence. Some physicists argue that the very existence of observers requires certain cosmic conditions, and those conditions naturally occur during a specific era of cosmic evolution. This is a version of what is called the anthropic principle. As the universe continues to expand and dark energy continues to dominate, what will ultimately happen? This depends on the exact nature of dark energy. If dark energy truly is the cosmological constant with unchanging density, then the universe will continue accelerating forever. Eventually, even protons might decay, given enough time. Current experiments have placed the proton lifetime at more than 10 to the power of 34 years. But some theories predict that all matter is ultimately unstable over vast enough timescales. If protons decay, then eventually all atoms will disintegrate. Stars, planets, even black holes will ultimately evaporate through Hawking radiation. The universe will become a cold, dark, empty expanse, populated only by photons, with wavelengths stretched to cosmic scales by the endless expansion. This scenario is sometimes called the heat death or big freeze. It is a universe of maximum entropy, where no more work can be done, no more complexity can emerge. Everything will be in thermodynamic equilibrium at a temperature just above absolute zero. Time will lose meaning because nothing will ever change. This is perhaps the most likely fate awaiting our universe based on current evidence. However, if dark energy is not constant, other possibilities emerge. If dark energy's density increases over time, the acceleration will become stronger and stronger. In the most extreme versions of these scenarios, called phantom energy models, the acceleration becomes so powerful that it eventually overcomes all forces, even the electromagnetic and nuclear forces that hold atoms together. This leads to the Big Rip. In a Big Rip scenario, the acceleration becomes infinite in finite time. First, galaxy clusters are torn apart. Then galaxies themselves are disrupted. Then solar systems are destroyed as planets are torn from their orbits. Then planets are ripped apart. Then molecules, atoms, and even atomic nuclei are torn apart. Finally, space itself is torn apart in a cosmic catastrophe. Some models suggest this could happen in as little as 20 billion years, though most evidence suggests it is not the likely fate of our universe. Alternatively, dark energy might weaken over time, or even reverse. If dark energy decreases, the universe's acceleration might slow or stop. If it reverses entirely, gravity could begin to dominate again, pulling everything back together. This leads to the Big Crunch, where the universe collapses back into a singularity, possibly followed by a new Big Bang in an endless cycle of expansion and contraction. However, current observations show no sign that dark energy is weakening. All evidence suggests that, if anything, the acceleration is strengthening over time. The illustrious simulation, one of the most sophisticated computer models of cosmic evolution, has been used to project how dark energy will shape the universe's future. The simulation starts with the conditions of the early universe shortly after the Big Bang and evolves forward, tracking how dark matter and ordinary matter clump together under gravity while space expands due to dark energy. The results paint a clear picture. The cosmic web of galaxy clusters and filaments that we see today is temporary. Over the next 100 billion years, this web will gradually dissolve. Clusters will disconnect from each other. Then individual galaxies within clusters that are not gravitationally bound will drift apart. Eventually, only the most tightly bound groups like our local group will remain, isolated in a vast and empty cosmos. What is particularly striking is how quickly this isolation happens from a cosmic perspective. The universe is currently about 13.8 billion years old. In just another 100 billion years, roughly 7 times the current age of the universe, the isolation will be complete. On cosmic timescales, this is relatively soon. We are living near the beginning of cosmic history, in the brief era when the universe is still connected and observable. The discovery of cosmic acceleration and dark energy has profound implications beyond just the ultimate fate of the universe. It changes how we think about space and time themselves. In Einstein's general relativity, gravity is not a force in the traditional sense, but rather a curvature of spacetime. Mass and energy curve spacetime, and objects move along the straightest possible paths through this curved spacetime. We perceive this motion as gravitational attraction. Dark energy adds a cosmic repulsion that acts on the larger scales, effectively adding a negative curvature or pressure to spacetime itself. This means that on cosmic scales, the shape of spacetime is dominated not by matter, but by dark energy. The geometry of the universe, whether it is flat, open, or closed, depends on the total energy density, including dark energy. Current measurements suggest the universe is very close to spatially flat, meaning that parallel lines remain parallel rather than converging or diverging. This flatness is maintained by a delicate balance between matter, and dark energy densities. Even a tiny change in these densities would have resulted in a universe that is either closed and would eventually collapse, or open and would have expanded so rapidly that no structures like galaxies could have formed. This brings us to another profound mystery connected to cosmic expansion. Why are the densities of matter and dark energy so finely balanced at this particular moment in cosmic history? In the early universe, matter and radiation dominated. Dark energy was negligible. In the far future, dark energy will completely dominate. We happen to live during the brief transition period when their densities are comparable. This seems like an extraordinary coincidence. Some physicists argue this is another manifestation of the anthropic principle. We observe this particular balance because we exist, and we can only exist during the narrow window when conditions permit complex structures like galaxies, stars, and planets to form. Others suggest this might be evidence of a multiverse. If there are countless universes with different properties, including different amounts of dark energy, then we naturally find ourselves in one of the rare universes where dark energy is just right for life to emerge. In most universes, dark energy would be either too large, preventing any structures from forming, or too small, allowing the universe to collapse quickly. Only in a tiny fraction of universes would the conditions be suitable for observers like us. This is a controversial idea because it is currently impossible to test, but it is taken seriously by many cosmologists as a possible explanation for what otherwise seems like an incredible cosmic coincidence. The measurements that revealed cosmic acceleration came from Type Ia supernovae, and understanding these cosmic explosions is crucial to understanding how we discovered dark energy. Type Ia supernovae occur when a white dwarf star, the remnant core of a sun-like star, accretes material from a companion star. When the white dwarf reaches a critical mass called the Chandrasekhar limit, about 1.4 times the mass of our Sun, it can no longer support itself against gravity. It collapses catastrophically, triggering a runaway thermonuclear explosion that completely destroys the star. Because all Type Ia supernovae involve white dwarfs reaching the same critical mass, they explode with approximately the same intrinsic brightness. This makes them ideal standard candles for measuring cosmic distances. By comparing a supernova's apparent brightness as we observe it with its known intrinsic brightness, we can calculate how far away it is. The farther away, the dimmer it appears, following a precise mathematical relationship. By also measuring the supernova's redshift, which tells us how fast its host galaxy is receding, we can plot distance versus recession velocity. The shape of this relationship reveals whether the expansion is accelerating or decelerating. When the Supernova Cosmology Project and the High Z Supernova Search Team performed these measurements in the late 1990s, they expected to find that distant supernovae were brighter than predicted for an accelerating universe. The mutual gravitational attraction of all matter in the universe should be slowing the expansion down, meaning distant galaxies in the past were receding more slowly than they are now. This would make them closer than expected, and therefore brighter. But the observations showed the opposite. Distant supernovae were dimmer, meaning they were farther away than expected. The only explanation was that the expansion had accelerated. Galaxies are now receding faster than they were in the past. The teams spent months checking their work. They considered every possible source of error. Could interstellar dust be dimming the distant supernovae? Could there be evolution in Type Ia supernovae properties over cosmic time making distant ones intrinsically dimmer? Could gravitational lensing be affecting the observations? Every possibility was investigated and ruled out. The conclusion was inescapable. The universe is accelerating. In 2011, the leaders of the two teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, were awarded the Nobel Prize in Physics for this discovery. Since then, cosmic acceleration has been confirmed by multiple independent methods. Measurements of the cosmic microwave background by the Wilkinson Microwave Anisotropy Probe and the Planck satellite show tiny temperature fluctuations that encode information about the universe's composition and expansion history. The pattern of these fluctuations is consistent with a universe dominated by dark energy. Measurements of baryon acoustic oscillations in galaxy clustering provide another independent confirmation. Observations of galaxy cluster evolution show how the growth of cosmic structure has been influenced by dark energy. Every method points to the same conclusion. The cosmic microwave background deserves special attention because it provides our most direct view of the early universe. About 380,000 years after the Big Bang, the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. Before this, the universe was filled with free electrons that constantly scattered photons, making the universe opaque, like being inside a cloud. Once atoms formed, photons could travel freely. The light from this moment has been traveling through space ever since, getting redshifted by cosmic expansion. Today, we detect it as microwave radiation with a temperature of about 2.7 Kelvin, just above absolute zero. The cosmic microwave background is remarkably uniform, with the same temperature in all directions, to better than 1 part in 100,000. But it is not perfectly uniform. There are tiny fluctuations in temperature. typically about 1 part in 100,000. These fluctuations are the seeds from which all cosmic structure grew. Slightly denser regions attracted more matter through gravity, growing over billions of years into the galaxy clusters we see today. The pattern of these fluctuations encodes information about the universe's composition, geometry, and expansion history. When we analyze these patterns, we find they match the predictions of a universe that is spatially flat and dominated by dark energy and dark matter. The size of the largest fluctuations tells us about the universe's geometry. The relative amplitude of fluctuations on different scales tells us about the relative amounts of different types of matter and energy. The way these fluctuations are distributed tells us about the expansion history. Every detail fits a model where dark energy accounts for about 68% of the total energy density, confirming what we learned from supernova observations. The sound waves that created the pattern in the cosmic microwave background also left an imprint on the distribution of galaxies today. In the hot, dense plasma of the early universe, pressure waves rippled outward from overdense regions at about half the speed of light. When atoms formed and the pressure support disappeared, these waves froze in place at a characteristic scale of about 500 million light-years. Today, we see a slight excess in the number of galaxy pairs separated by this distance. This is the baryon acoustic oscillation signal, a relic of sound waves from the early universe. By measuring how this characteristic scale appears at different redshifts, we can trace the expansion history of the universe with great precision. If the universe were expanding at a constant rate, the scale would appear the same at all distances. If the expansion were decelerating, it would appear smaller at large distances. If the expansion is accelerating, it appears larger. Observations by the baryon oscillation, spectroscopic survey, and other projects confirm the acceleration discovered by supernova observations. Multiple independent methods all point to dark energy being real. Let us now consider the earlier history of cosmic expansion before dark energy became dominant. In the first few seconds after the Big Bang, the universe was unimaginably hot and dense. In these conditions, all 4 fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, behaved very differently than they do today. At extremely high energies, these forces may have been unified into a single force, a grand unified theory that we have yet to discover. As the universe expanded and cooled, these forces separated in a process called symmetry breaking, like how liquid water crystallizes into structured ice. Each symmetry breaking released enormous energy and triggered phase transitions in the quantum fields that permeate space. These phase transitions had profound effects on the universe's evolution. One particular phase transition, occurring perhaps 10 to the power of -35 seconds after the Big Bang, triggered something called cosmic inflation. Cosmic inflation is a period of exponentially rapid expansion that occurred very early in the universe's history. During inflation, the universe expanded by a factor of at least 10 to the power of 26 in a tiny fraction of a second, possibly much more. This sounds similar to the current dark energy-driven acceleration, and indeed both involve the energy of empty space driving expansion. However, inflation was far more intense and occurred over a much shorter timescale. And unlike the current acceleration, which will continue forever, inflation ended when the field driving it decayed, releasing its energy as ordinary matter and radiation. Cosmic inflation solves several major problems in cosmology. It explains why the universe is so uniform. Regions that are now on opposite sides of the observable universe, too far apart to have ever been in contact, have the same temperature and properties. How could they be so similar if they were never able to exchange information. Inflation solves this by proposing that all regions we see were once in close contact, in thermal equilibrium. Inflation then stretched them to cosmic scales. The uniformity we observe is because everything came from the same tiny region that was inflated to enormous size. Inflation also explains why the universe is so flat. The geometry of space depends on its total energy density. If the density is exactly at a critical value, space is flat. If it is higher, space curves back on itself like the surface of a sphere. If it is lower, space curves outward like a saddle. The universe today is flat to better than 1% precision. But any deviation from exact flatness grows exponentially with time. For the universe to be as flat as we observe today, it must have been incredibly, impossibly flat in the early universe, fine-tuned to something like 1 part in 10 to the power of 60. Inflation solves this problem by making the universe so large that the part we can see is just a tiny patch of a much larger whole, so large that any curvature is undetectable, like how the surface of the Earth appears flat when you are standing on it, even though the Earth is a sphere. Inflation also explains the origin of cosmic structure. The tiny temperature fluctuations we see in the cosmic microwave background, the seeds from which galaxies grew, originated as quantum fluctuations during inflation. In quantum mechanics, all fields fluctuate randomly on microscopic scales due to Heisenberg's uncertainty principle. During inflation, these quantum fluctuations were stretched to cosmic scales and frozen in place. When inflation ended, these fluctuations became density variations in matter. Denser regions attracted more matter and grew into galaxies. The largest structures we see today, galaxy clusters and the cosmic web, all grew from quantum fluctuations inflated to cosmic size. This is one of the most remarkable predictions of inflation theory, and has been confirmed by observations of the cosmic microwave background. However, while inflation explains many features of the universe, it also raises new questions. What field drove inflation? What triggered it? Why did it end? Different inflation models give different answers, and we do not yet know which, if any, is correct. Inflation also predicts that our observable universe is just a tiny part of a vastly larger, possibly infinite space. Moreover, in most inflation models, inflation never completely ends. It continues in some regions of space while ending in others. This leads to the concept of eternal inflation and the multiverse, where countless bubble universes form, each with potentially different physical laws and properties. If the multiverse exists, it would have profound implications for our understanding of dark energy and cosmic expansion. The amount of dark energy in our universe might not be the result of fundamental physics, but rather an environmental accident, one value among countless others realized in different bubble universes. We observe the value we do because it is consistent with our existence. This would explain the otherwise mysterious coincidence that dark energy is so finely tuned to allow structure formation. But let us return to more solid ground and consider what we can directly observe about cosmic expansion. One of the most important observations is the redshift of distant galaxies. When light travels through expanding space, its wavelength gets stretched. This stretching shifts light toward longer wavelengths, toward the red end of the spectrum. The amount of redshift tells us how much the universe has expanded since the light was emitted. Redshift is quantified by a number called z. A redshift of 0 means no expansion. The object is at rest relative to us. A redshift of 1 means the universe has doubled in size since the light was emitted. A redshift of 2 means it has tripled in size. The most distant galaxies we have observed have redshifts above 10. meaning the universe has expanded by a factor of more than 11 since their light was emitted. These galaxies appear as they were less than 500 million years after the Big Bang, when the first stars and galaxies were just forming. The James Webb Space Telescope has observed galaxies at even higher redshifts, pushing back to just a few hundred million years after the Big Bang. These observations reveal surprising facts about the early universe. Galaxies formed earlier and grew faster than many models predicted. Some early galaxies are more massive and structured than expected, challenging our understanding of how galaxies form and evolve. These observations are still being analyzed and debated, but they demonstrate that we still have much to learn about cosmic history. By measuring redshifts for thousands of galaxies at different distances, astronomers have reconstructed the expansion history of the universe in remarkable detail. This history shows several distinct eras. In the first few minutes after the Big Bang, the universe was hot enough for nuclear fusion to occur throughout space. Protons fused into helium and trace amounts of heavier elements. This era of Big Bang nucleosynthesis lasted only about 17 minutes, but it determined the relative abundances of hydrogen and helium that we observe throughout the universe. About 75% hydrogen and 25% helium by mass, with tiny traces of lithium and other light elements. For the next few 100,000 years, the universe was dominated by radiation, meaning photons carried most of the energy. Matter and radiation were coupled together in a hot plasma. The universe was opaque because photons constantly scattered off free electrons. Then, about 380,000 years after the Big Bang, the universe cooled enough for atoms to form. This is called recombination, even though it is the first time atoms formed and not actually a recombination. Once atoms formed, photons could travel freely, and the universe became transparent. This is the light we see as the cosmic microwave background. After recombination, the universe entered what is sometimes called the Dark Ages. No stars had formed yet, and the only light was the fading glow of the cosmic microwave background, being redshifted to longer and longer wavelengths. The first stars formed perhaps 100 to 200 million years after the Big Bang, ending the Dark Ages. These first stars were very different from stars today. They formed from gas that contained only hydrogen and helium, no heavier elements because no stars had existed to create them. Without heavier elements, the gas could not cool as efficiently, so the first stars were likely extremely massive, perhaps hundreds of times the mass of our Sun. These massive stars lived fast and died young, exploding as supernovae after only a few million years. These explosions synthesized heavier elements and scattered them into space, enriching the gas from which the next generation of stars formed. Over billions of years, successive generations of stars gradually increased the abundance of heavy elements, creating the rich chemical complexity we see today. Every carbon, nitrogen, oxygen, iron, and gold atom in our bodies was created by nuclear reactions in stars and supernova explosions billions of years ago. We are, quite literally, made of star stuff. As the first stars formed and galaxies began to assemble, dark matter played a crucial role. Dark matter does not emit, absorb, or scatter light, making it invisible to telescopes. We detect it only through its gravitational effects. Galaxies rotate faster than the visible matter alone can explain. Galaxy clusters contain much more mass than we can see in stars and gas. Gravitational lensing, where light is bent by gravity, reveals invisible mass. All evidence points to dark matter being the dominant form of matter in the universe, about 5 times more abundant than ordinary matter. Dark matter forms the scaffolding on which visible structures grow. In the early universe, dark matter clumped under its own gravity, forming vast halos. Ordinary matter fell into these halos and concentrated at their centers, forming galaxies. Without dark matter, galaxies would not have formed, at least not in the time available. The universe is only about 13.8 billion years old. Gravity acting on ordinary matter alone would not have had time to pull together galaxy-sized structures from the nearly uniform conditions of the early universe. Dark matter, unimpeded by pressure forces that affect ordinary matter, clumped faster and provided the gravitational seeds around which galaxies formed. What is dark matter made of? We do not know. The most popular hypothesis is that dark matter consists of weakly interacting massive particles, or WIMPs. These would be new particles predicted by extensions to the standard model of particle physics, particles that interact only through gravity, and possibly the weak nuclear force. Despite extensive searches using underground detectors, particle accelerators, and space-based telescopes, dark matter particles have not been directly detected. This has led some physicists to consider alternative explanations, such as modifications to our theory of gravity, or more exotic particles like axions or sterile neutrinos. Regardless of what dark matter is made of, its gravitational effects on cosmic expansion are clear. Dark matter slows expansion through its gravity. In the early universe, when matter and dark matter were more dense, their gravitational pull was stronger relative to dark energy, and the expansion was decelerating. As the universe expanded and became more diffuse, dark energy became relatively more important. About 5 billion years ago, dark energy began to dominate, and the expansion began accelerating. This transition from deceleration to acceleration is written in the distribution of galaxies across cosmic time. By mapping galaxies at different distances, and therefore different cosmic epochs, we can trace how structure formation has evolved. In the early universe, small fluctuations in density grew rapidly as gravity pulled matter together. Galaxy formation proceeded vigorously as matter clumped into dense regions. But as dark energy became dominant, the expansion accelerated and structure formation slowed. Galaxies continued to grow and evolve, but the large-scale cosmic web stopped growing. Future galaxy clusters will not form because cosmic expansion is pulling potential members apart faster than gravity can bring them together. The Sloan Digital Sky Survey has created three-dimensional maps of millions of galaxies, revealing the cosmic web in unprecedented detail. We see vast filaments of galaxies stretching hundreds of millions of light years, surrounding enormous voids where few galaxies exist. These voids are not empty in the sense of containing no matter. They contain dark matter and gas, but the density is so low that few galaxies formed there. The contrast between dense filaments and empty voids is the large-scale structure of the universe, the cosmic web that grew from tiny quantum fluctuations in the first moments after the Big Bang. This cosmic web is not static. Galaxies move within it, falling along filaments toward dense clusters. Galaxy clusters themselves occasionally collide, creating spectacular fireworks as hot gas in one cluster smashes into gas in another. The Bullet Cluster, two galaxy clusters that collided about 150 million years ago, provides some of the strongest evidence for dark matter. The hot gas in the clusters, which we can see through X-ray telescopes, interacted and slowed during the collision. But the dark matter, which interacts only gravitationally, passed through unimpeded. Gravitational lensing reveals that most of the mass is now separated from the gas, showing that dark matter and ordinary matter behave differently, and confirming that dark matter is not just gas or stars we cannot see. As we look to the distant future of cosmic expansion, several possible scenarios emerge, depending on the exact nature of dark energy. If dark energy is the cosmological constant, with unchanging density, then the universe will continue accelerating forever. This seems to be what observations favor, though we cannot be completely certain. In this scenario, the eventual fate is the heat death or big freeze. Over the next 100 billion years, galaxies outside our local group will disappear beyond the cosmic horizon. Our local group will merge into Milkomeda. Star formation will continue for a while, using the remaining gas. But eventually, all gas will be used up or expelled. The last stars will burn out. The universe will be filled with white dwarfs, neutron stars, and black holes in an ever-expanding space. White dwarfs will slowly cool, radiating away their heat over trillions of years until they become cold, dark black dwarfs. Neutron stars will similarly cool. Black holes will slowly evaporate through Hawking radiation. A black hole radiates because quantum effects near the event horizon allow particle-antiparticle pairs to form, with one member falling into the black hole and the other escaping. This process gradually decreases the black hole's mass. For a stellar mass black hole, this takes an unimaginably long time, something like 10 to the power of 67 years. For supermassive black holes like those at galaxy centers, even longer. Eventually, perhaps after 10 to the power of 100 years, even the largest black holes will have evaporated. The universe will contain only photons, neutrinos, and perhaps other stable particles like electrons and positrons, all with wavelengths stretched to cosmic scales by the endless expansion. The temperature will be a tiny fraction above absolute zero. Nothing interesting will ever happen again. This is perhaps the most likely ultimate fate of the universe, based on current evidence, though it is so far in the future that likely must be taken with appropriate uncertainty. If dark energy's density increases over time, as in phantom energy models, the acceleration will strengthen. In extreme cases, this leads to the Big Rip. As the universe accelerates more and more rapidly, the cosmic horizon shrinks. Objects that are currently bound together will be torn apart as space expands faster and faster between them. First, galaxy clusters are disrupted, then galaxies, then solar systems as planets are torn from their stars. Then planets themselves are torn apart as expansion overcomes the electromagnetic forces binding rock and iron. Then molecules, then atoms, then atomic nuclei, as even the strong nuclear force is overcome. Finally, space-time itself may be torn apart in a singularity. Some models suggest a Big Rip could occur in as little as 20 billion years, though most evidence suggests phantom energy is not what drives our universe's expansion. The fact that dark energy appears constant, rather than increasing, over time argues against the Big Rip scenario. However, we have only been measuring dark energy for a few decades, a tiny fraction of cosmic history. We cannot be absolutely certain it will remain constant forever. Alternatively, if dark energy weakens or reverses, the expansion could slow and eventually reverse, leading to the Big Crunch. In this scenario, the universe reaches a maximum size and then begins contracting. All the structures that formed during expansion are gradually pulled back together. The cosmic microwave background becomes blue-shifted, heating up as space contracts. Eventually, galaxies merge, then stars collide, and finally everything is crushed back into a singularity similar to the Big Bang, but in reverse. Some models suggest this could be followed by a new Big Bang, creating an oscillating universe that expands and contracts in endless cycles. The Big Crunch was once thought to be the likely fate of the universe before dark energy was discovered. If the universe contained enough matter, its gravity would eventually overcome the expansion and pull everything back together. But we now know that dark energy exists, and is accelerating the expansion. Unless dark energy reverses, which we see no evidence for, the Big Crunch will not occur. One fascinating possibility is that the universe could undergo a phase transition in the far future, similar to the phase transitions of the early universe. The quantum fields that permeate space exist in particular states determined by their energy. It is possible these fields are not in their absolute lowest energy state, but rather in a metastable state, like a ball sitting in a small valley on the side of a mountain. The ball is stable for now, but it is not in the lowest possible position. If it were nudged, it would roll down to a much lower valley. If the Higgs field or other quantum fields in our universe are metastable, a quantum tunneling event could trigger a transition to the true lowest energy state. This transition would create a bubble that expands at the speed of light, converting space inside the bubble to the new, lower energy state. Everything inside the bubble would be restructured as the fields changed their values. The laws of physics might be different. Atoms might not exist. The transition would be catastrophic, destroying everything in its path. The expanding bubble would eventually encompass the entire universe. How likely is this? We do not know. The stability of the Higgs field depends on its precise properties and its interactions with other fields, which we have not measured with perfect precision. Current measurements suggest the Higgs field might be metastable, meaning it is stable for now but could decay given enough time. If it is metastable, the timescale for decay could be extraordinarily long, far longer than the current age of the universe, or it could happen tomorrow. We simply do not know. Such a transition could have already occurred somewhere in the observable universe, with a bubble of altered physics expanding toward us at the speed of light. We would have no warning. The bubble would arrive at the speed of light, and we would be destroyed instantaneously. This might sound like the plot of a science fiction novel, but it is a real possibility considered seriously by physicists. The vacuum state of quantum fields is not necessarily stable, and we cannot rule out the possibility of a phase transition. However, the universe has existed for nearly 14 billion years without such a transition occurring in our region of space, which suggests either the fields are truly stable, or the metastable state is long-lived enough that a transition is extremely unlikely on any timescale relevant to humanity. Let us step back and consider what all of this means for our place in the universe. We live in an expanding universe, driven by dark energy toward an isolated, cold future. We exist during a narrow window of cosmic time, when the universe is old enough for complex structures and intelligent life to exist, but young enough that the universe's history is still visible and comprehensible. This is not an accident. The conditions that allow life to exist are closely connected to the conditions that allow the universe to be understood. Stars must exist long enough for planets to form and life to evolve. This requires a universe old enough for multiple generations of stars to have lived and died, enriching space with heavy elements. But the universe cannot be too old, or all stars will have burned out. We must exist while stars are still shining. Similarly, the expansion rate must be just right. If expansion were much faster, galaxies would never have formed. If it were much slower, the universe might have collapsed before stars and planets could form. The fact that we exist to observe the universe means we must observe it during the narrow era when conditions permit our existence. This is the essence of the anthropic principle, and it applies to many aspects of the universe, not just cosmic expansion. The strength of gravity must be just right for stars to form and burn steadily. The electromagnetic force must be just right for chemistry to work. The strong nuclear force must be just right for atomic nuclei to be stable. Change any of these constants by even a small amount, and the universe would be radically different. likely unable to support life. Some physicists argue this fine-tuning is evidence of design or purpose. Others argue it is evidence of a multiverse where all possible values occur, and we observe the particular combination that permits our existence. Still, others argue we do not yet understand the deep principles that determine these constants. And once we do, we will understand why they must have the values they have. Regardless of the explanation, the fact remains that we live in a universe that permits us to exist and to understand our existence. This is a profound privilege and responsibility. We have the ability to trace cosmic history back to the first moments after the Big Bang, to understand the laws of physics that govern reality, to predict the ultimate fate of the universe billions of years hence. No other species on Earth has this capability. We do not know if any other species in the universe has achieved this level of understanding. We might be alone, or we might be one of countless civilizations. But either way, we have a unique perspective on the cosmos. The expansion of the universe, driven by mysterious dark energy, is one of the most profound discoveries in the history of science. It tells us that the universe had a beginning, that it is evolving, and that it will have an end of sorts, though not the kind of dramatic end our ancestors imagined. The universe will not end in fire, but in ice, slowly fading as expansion stretches everything to cosmic scales and cools everything to near absolute zero. This fate is still trillions of years away, an almost incomprehensible span of time. Humanity, if we survive, will have eons to explore, to create, to understand. The expanding universe does not diminish our significance. If anything, it amplifies it, showing that we are part of something vast and ancient, something that began in a singularity and will end in cold darkness, but in between contains beauty, complexity, and consciousness. The question, why does the universe expand, has multiple layers of answers. The immediate answer is that space itself is expanding, driven by the initial impetus of the Big Bang, and more recently, accelerated by dark energy. The deeper answer is that expansion is built into the fabric of spacetime through Einstein's equations of general relativity. Mass and energy curve spacetime, but they also allow spacetime to expand or contract. In a universe with matter and energy distributed uniformly on large scales, expansion is a natural solution to these equations. The deepest answer, which we do not yet fully understand, involves the quantum fields that permeate space and the mysterious vacuum energy we call dark energy. Why does this energy exist? Why does it have the particular density we observe? These questions remain at the frontier of physics. Some theorists have suggested that dark energy might not be a fundamental property of space, but rather a side effect of modifications to gravity on cosmic scales. Einstein's general relativity works extremely well in the solar system and even around black holes, but perhaps it breaks down on the scale of billions of light years. Modified gravity theories attempt to explain cosmic acceleration without invoking dark energy. However, these theories have difficulty matching all the observations, particularly the detailed pattern of the cosmic microwave background and the growth of cosmic structure. Most physicists believe dark energy is real, even if we do not understand what it is. Another possibility is that what we interpret as dark energy is actually a clue that the universe is more than four-dimensional. String theory, a leading candidate for a theory of quantum gravity, suggests that space might have additional dimensions beyond the three we perceive. These extra dimensions would be curled up so small that we cannot detect them directly, but they could affect gravity on cosmic scales. In some string theory models, our universe is a three-dimensional membrane floating in a higher dimensional space, and what we interpret as dark energy is the influence of this higher dimensional space on our membrane. These ideas are highly speculative and difficult to test, but they illustrate how the mystery of dark energy might be connected to even deeper mysteries about the nature of space and time. As we continue to observe the universe with increasingly sophisticated instruments, our understanding of cosmic expansion will deepen. Future missions like the Nancy Grace Roman Space Telescope will map millions of galaxies with unprecedented precision, tracing the expansion history and the growth of structure in exquisite detail. Ground-based surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time will monitor billions of galaxies over a decade, watching cosmic evolution in real time. These observations might reveal subtle deviations from the simple model of a constant cosmological constant, giving us clues about the true nature of dark energy. We might discover that dark energy is changing over time, which would revolutionize our understanding and alter predictions for the universe's ultimate fate. We might find evidence for modifications to gravity or for extra dimensions. We might even find hints of other universes through their gravitational influence on our own, though this seems unlikely. More likely, we will refine our measurements, constrain the possibilities, and rule out alternatives until we narrow down what dark energy must be, even if we cannot yet explain why it exists. The story of cosmic expansion is a story of discovery and mystery, of elegant mathematics and perplexing observations. It is a story that connects the smallest scales, quantum fluctuations inflated to cosmic size, to the largest scales, the ultimate fate of the entire universe. It is a story that began with the Big Bang nearly 14 billion years ago and will continue for trillions of years into the future. And it is a story in which we, briefly, play a part, conscious observers trying to understand the vast cosmic drama in which we find ourselves. Understanding cosmic expansion requires us to think about space and time in unfamiliar ways. Space is not a fixed stage on which events occur. It is a dynamic entity that can expand, contract, and curve. Time is not absolute but relative, flowing at different rates depending on gravity and motion. These concepts, which seemed radical when Einstein proposed them, are now confirmed by countless experiments and observations. The expanding universe is perhaps the most dramatic demonstration that space and time are not what our everyday experience suggests. They are fluid, changeable, and deeply interconnected with the matter and energy they contain. When we say the universe is expanding, we mean that the distance between any 2 points in space that are not bound together by local forces is increasing over time. This is not because those points are moving through space, but because new space is being created between them. An analogy that is often used, though imperfect, is the surface of an inflating balloon. Dots drawn on the balloon move apart as it inflates, but the dots are not moving across the rubber. The rubber itself is stretching. Similarly, galaxies are not flying through space. Space itself is expanding, carrying galaxies along with it. This might seem like a meaningless distinction, but it has important consequences. One is that objects can recede faster than light without violating relativity, as we discussed earlier. Another is that the expansion rate can change over time without violating any conservation laws. When space expands, it is not converting energy from one form to another. It is creating new space with its associated vacuum energy. This might seem to violate energy conservation, but in general relativity, energy conservation is not a fundamental law in an expanding or contracting universe. Energy can be created or destroyed as space expands or contracts. This is one of the more conceptually challenging aspects of cosmology, but it is a necessary consequence of taking general relativity seriously in an expanding universe. The ultimate question, perhaps, is not just how the universe expands, but why it exists at all. Why is there something rather than nothing? Why does the universe have the particular properties it does, the particular laws of physics, the particular values of fundamental constants? These questions go beyond cosmology into philosophy and metaphysics. Science can trace the universe's evolution back to a tiny fraction of a second after the Big Bang. But the moment of the Big Bang itself, and anything that might have come before, remains mysterious. Some theories suggest the universe arose from a quantum fluctuation, a random event allowed by the uncertainty principle. In quantum mechanics, energy can be borrowed from nothing for brief moments, constrained by the relationship between energy and time in Heisenberg's uncertainty principle. Perhaps the entire universe is such a quantum fluctuation, an enormous borrowing of energy that has not yet been repaid, because the universe is still young. This is a speculative idea, but it illustrates how quantum mechanics might play a role in the universe's origin. Other theories suggest the universe might be eternal, with no true beginning, undergoing endless cycles of expansion and contraction, or budding off from other universes in an eternal process of cosmic reproduction. Still, others suggest the universe was created by some process we do not yet understand, perhaps in a higher dimensional space, or through mechanisms we have not yet imagined. These ideas are fascinating, but difficult to test, because by definition, we cannot observe anything before or outside our universe. What we can observe is the universe we have, with its expansion, its dark energy, its dark matter, and its elegant laws of physics. We can trace its history, predict its future, and marvel at the fact that we exist within it, able to comprehend it. The expanding universe is not just a scientific fact. It is a profound truth about the nature of reality, a truth that changes how we understand our place in existence. We are temporary inhabitants of a universe that will long outlast us, but we are also privileged witnesses to a cosmic story that spans from the Big Bang to the heat death, from quantum fluctuations to galaxy clusters, from singularity to entropy. In understanding cosmic expansion, we understand the fundamental nature of space, time, matter, and energy. We understand our origins and our fate, as individuals, as a species, as part of the vast cosmic tapestry. And perhaps most importantly, we understand that the universe is comprehensible, that through observation, reason, and mathematics, we can decode its secrets and glimpse the deep structure of reality itself. This is the gift of cosmic expansion, not just knowledge of how the universe evolves, but proof that the universe can be known.